All right, so we want to start today just by kind of getting a handle on what it means when we graph just on our Cartesian plane, our XY coordinates, which you have been doing for many years now, right? So when I get to this point, A right here, that what we're able to do when we're graphing is we're able to share information with the entire world as to where that point is, right? So graphing allows us to transmit information about location. So once we know where the X and the Y coordinates are, and we tell someone that point A is located at the ordered pair 3, 4, right? Then everybody can know exactly where to go. And so we know from our vast experience in graphing on the Cartesian coordinate plane that this means to go to the right 3 and then up 4, and this is the spot we want to be at. Right? So it's a way of communicating location. Now, we have other methods of communicating location, like think about having longitude and latitude. That's another way to communicate a location. Well, mathematically, besides this Cartesian coordinate plane, which, so just remember, I'm saying this word, Cartesian. It's called the Cartesian coordinate plane. It's named after the mathematician and philosopher René Descartes. We also sometimes refer to this as rectangular coordinates. Okay? But mathematically, there is an entirely other way of telling someone how to get to point A. So in our rectangular or our Cartesian coordinate plane, we're giving them an X distance, which is horizontal, followed by a Y distance, which is vertical. We all know to start at the origin, and then we know exactly where to go. Well, the other way of graphing is referred to as polar. And in a polar system, we don't have an X and a Y axis anymore. But in a polar system, we do have this point here, which we normally refer to as the origin. It is called the pole, right? And then our x-axis is where we begin measuring an angle. And so then if I were to start at the pole and go out to point A and create this vector, right? I know that I can describe this vector by telling you its angle of direction, theta, as well as its magnitude, right? So we know vectors have direction and magnitude. So we've talked about the magnitude of a vector. So isn't it true that if I told you the angle of direction and I told you the magnitude of the vector, and then I said find the terminal point, you could get there to point A, right? You just say, well, my angle goes like this, then my magnitude goes out this far, and it stops right there, and so you could get there. So the one switch that we're going to make is we're going to call this magnitude of the vector is a lowercase r. And that kind of relates to the idea of a radius, the radius on our unit circle. And so this point A, in polar coordinates, we list it as r comma theta. Right? So in rectangular or Cartesian coordinates, we have point A is xy. Well, in our polar coordinates, it's r, which is really the magnitude of this vector, and then theta, which is the angle, the directional angle. So if I have this ordered pair, 3, 4, and I know what it is in rectangular, but I wanted to know what my r and theta were in polar, I'm just going to apply some knowledge that I've already learned about vectors, right? So look at that distance of r. Didn't we find the magnitude by relating it back to the distance formula or the Pythagorean theorem? So we know that r squared is equal to x squared plus y squared. Right? So we have a right triangle there, Pythagorean theorem. So then taking the square root of both sides, we know that r is the square root of x squared plus y squared. So for this particular case, r would be the square root of 3 squared plus 4 squared. And we know that 3 squared is 9, and 4 squared is 16, and 9 added with 16 is 25, and the square root of 25 is 5. So our r would be 5. Well, we also learned how to find this directional angle when we were studying vectors. So remember that for that, we went back to our right triangle trigonometry of SOHCAHTOA. And in relation to theta, y is my opposite side and x is my adjacent side. So I would use tangent, and I would say that tangent of theta is equal to opposite over adjacent. So for this particular problem, the tangent of theta would be my opposite side, which is 4, over my adjacent side, which is 3. And then I would take the inverse tangent of both sides. And for that, I would use my calculator. And I would do inverse tangent, 4 divided by 3, 53.1 degrees. So this point in space, 3, 4, on the rectangular coordinate system, is at the exact same spot as 53.1 degrees on the polar coordinate plane. So the way we graph if we're given polar coordinates is a little weird because we're usually reading from left to right. Well, when you're graphing a polar coordinate, you actually start with your angle, right? So I start here at my angle. I'd measure out 53.1 degrees. And then I would start here and I would go on that path 5 units until I got to that point. So that's the relationship between polar and rectangular. And so look at how you would, we used a specific example, but anytime you wanted to take a rectangular point and switch it to polar, you're going to come in here and use your Pythagorean theorem. I guess really all of this. So you can get R, and then you're going to use your tangent relationship so that you can get theta. Well, what if we knew R and theta and we wanted to know the rectangular form? Okay. Well, that's also pretty easy with everything we've learned this year. So, if I want the rectangular form, that means I need to express x some kind of a way. Well, I need to express x in terms of r and theta. So if I'm going to look at x and r in right triangle trigonometry, x is my adjacent, r is my hypotenuse. Adjacent and hypotenuse is related with cosine. So I could say the cosine of theta is equal to x over r. There's my theta. It's adjacent over hypotenuse. So then if I multiply both sides by r, I have r cosine theta is equal to x. So if I were starting with a polar coordinate, I could plug in my r and my theta and get to x. Let's just test it with this one we just did. So I want to make sure that we're in degrees. So if r is 5, and then I multiply by the cosine of 53.1 degrees, there's 3. That's my x value. All right. Well, how can I define y in terms of theta and r? So again, right triangle trigonometry, if this is theta, y is my opposite. Opposite over hypotenuse is related with the sine. So sine of theta is y over r, opposite over hypotenuse. Multiplying both sides by r sine theta is equal to y. Again, if I take the example that I had, and I do 5 times the sine of 53.1, and if I were to round that to the nearest whole number, I would be at 4. So there's my ordered pair, 3, 4. Right, so that shows you how to convert. If you're starting with rectangular, you can convert over to polar. If you're starting with polar, you can convert back to rectangular. All right. Let's just say that we had a point and we wanted to graph it in polar. So let's just say that I gave you the point 3, 45 degrees. So how would you go about plotting that point? So again, you're going to start with your degrees. So you'd start and you'd say, well, let's see, this is 90 degrees up here, so 45 degrees is on this path, right? And then we need to go out 3 units. Well, remember, on your diagonal, that's not 1 unit, because this is 1 and this is 1, so this is actually the square root of 2. So when we graph with polar coordinates, we actually have a coordinate system that's made of these concentric circles. So if I go out to radius 1, 1, 1, 1, and make a circle, so then when I'm going out 45 degrees and I want a radius 1, it just touches that circle. So if I go out to radius 2, radius 2, radius 2, radius 2, so there's where 2 is. So if I go out to radius 3, radius 3, radius 3, radius 3, map out a circle there. So 45 degrees and radius 3, 1, 2, 3, that's my point. So if this is point B, that's point B right there. So let's do another point. What if I had point C and it was at 180 degrees? So again, I'm starting here, measuring counterclockwise. Remember, that's how we measure angles, counterclockwise, to 180 degrees, and then go out to a radius of 2. That's point C right there. All right. What if I had point D, and point D was at 1, and 225 degrees? So again, I start with my directional angle. So I'm going to start here. I'm going to go around 225 degrees is 45 degrees past 180, but my radius is only 1. So point D is right there. All right, now watch this though. What if I said, what if I had point E? And what if point E was at -1, 225 degrees? So then I'm gonna take my angle, measure around to 225 degrees, but then if my radius is negative, I basically have to start at my pole and go backwards. So point E is here. Now, one last interesting thing about polar coordinates. This point B is at 345 degrees. That's true. But that is not a unique ordered pair, right? Because remember, polar coordinates or angles go around and around and around and around. So point B is also at 3, and then if I take 45 degrees and I go around 360 more, 405 degrees. Because if I was here and I went around 360 plus 45 more, that would be 45 degrees, and then I go radius 3, I'm going to land there at point B again. And then I could add another 360 and another 360 and another 360. So anytime I have 3 for my radius and I have 45 degrees plus some multiple of 360 degrees. So 360 degrees times any integer, that will land me on that exact same point B.